So just want to give you guys a chance to do some naming on your own. So if you look there, I've got 3 different examples on there. Give you a moment to draw them, to name them, to contemplate their existence. You want to wax, poetic there. Okay, so if we look at this first one, what's the root word going to be? 8, which would be octane. So we have octane. Okay, and now we have to think about all the different functional groups. So we have, let me do this one. So there's 1, 2, 3, 4, 5, 6, 7, 8. Because for those who, because otherwise some people may have come up with 7. Okay, so we have this functional group, this one, and this one. So what's the name of this one going to be? That's a methyl, and this one would be methyl, ethyl, and methyl. So we have 3 methyls and an ethyl. Alrighty. So which one comes last in the alphabetical order, because it's the one that's going to be closest to the root word, because that's how I have to do it for spacing. Methyl. So we just write out the methyl. What else do we need to put with methyl here? Tri. Okay, and then we have to give the locants. What will be the locants for the methyls? 3, 4, 6. So there's 3, 4, 6. Is there anything else that we could do? 3, 4. Actually, I hadn't counted it. Yeah, that's why I'm so. It was 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6. So it's 3, 5, 6. Good. Sometimes I've put some up there that were way off since I jumped off it. All right, and then we have ethyl. Notice once again, you would not have to say mono or for 1, because it's just assumed if you write it in there and there's 1. And then what would be the locant for it? It's 4. So we have 4 ethyl, 3, 5, 6 trimethyloctane. Once again, I would expect you to be able, at this point in time, be able to go backwards. If I gave you the name, that you'd be able to draw it. Now, the second example there, what would its name be? It's hexane. Okay. So then, what about the next one down below? Cyclohexane. So that's why I wanted to show you. There's 6. It still has only single bonds in it, but we have to differentiate the fact that it's cyclic, and so you put the prefix cyclo on it. So it's relatively simple. So now, give me a moment to draw these. Name them on your own. Okay, so what's going to be the root on this one? So is it going to be cyclopropane, or what's the other possibility? Pentane. So now we have to ask ourselves, which is bigger? The cyclopropane, which has 3 carbons, or the pentane has 5? The pentane has 5, so pentane gets priority over that. Okay? And so pentane is actually going to be the root. And that means that the cyclopropane is actually going to be the functional group, the substituent hanging off. And so what's the ending that we've been putting, what's that called? The suffix that we've been putting on all of the groups that are hanging off of something? YL, ill, right, YL. And so when it was one carbon, it was methyl. 2 carbons was ethyl. Instead of ethane, became ethyl. So this won't be cyclopropane, but it will become cyclopropyl. Okay, and then we have to finally give it a locant, and the number it would be 2. So it's 2-cyclopropylpentane. Okay, the next we're going to actually start functional groups a little bit. The book here only gives you their common names, which I think is sad that they didn't go ahead and jump in and start to talk a little bit about how to number them and everything like that. But functional groups, the first 2 functional groups, and every organic chemistry book that I know I've ever used to start off with, are alcohols and alkyl halides. Okay, and so an alkyl halide has a generic form that they like to say is called RX. R just means it's any carbon-containing group. Okay, so it could be a methyl group with a chlorine hanging off of it. It could be a cyclohexyl group with a bromine hanging off of it, anything like that. Okay, so that's that's an alkyl halide. And then we have alcohols. And an alcohol, once again, it's going to have some type of carbon group, of course. But what's the functional group? Hopefully you started looking up your functional groups. What's a functional group for an alcohol? OH. It's a hydroxyl. Okay. And so, for example, we have this one, or we can have I can give you their common names. But I also want you to learn how to start using their substitutive names. Like their official IUPAC names, I should say. So on the top one is an alkyl halide. Okay? And so how many carbons are hanging off the or the bromine is hanging off whichever. How many carbons are there in that compound? They're just 2, okay? Because that bromine is, the way that's drawn, that is drawn where the bromine is directly off the one that kind of is pointing up. It's off of this one. So there's 1, 2. Okay? And so the common name for it is ethyl bromide. However, if you think back to Gen Chem, like we had like sodium bromide or sodium chloride, that kind of indicated it was a metal, was a non-metal. Well, that ethyl is not a metal; it's a covalent compound. So the common name is ethyl bromide. But I'm going to also teach you how to do the using the IUPAC name right now. So the longest carbon-containing chain would be called, what would its name be? Like if the bromine wasn't there, what would you call that? How many carbons does it have? 2, and so it would be called ethane. So that's the same. Ethane. And now the bromine is the substituent hanging off of it. And so we don't say bromyl for halogens, we use the O. It becomes bromo. Just like iodine would be iodo, chlorine is chloro. Fluorine is fluoro. And if you have more than one, you have di or tri or some. You normally would have to give locant. You don't have to here because there's only one place. Like you can only have 1 bromoethane. Now if we had put 2 on there, so if I wanted to up the ante a little bit, then that becomes dibromoethane, and you have to give the locant, so it'd be 1, 2. Does that make sense? Because you have one hanging off of carbon number 1, we have one hanging off of carbon number 2. So it's 1, 2 dibromoethane. Okay, now the one on the bottom, if the alcohol wasn't there, what would it be called? Cyclopentane, okay? Don't write out the don't write it all the way out. I'm just going to show you something. So cyclopentane, alcohol gets priority, so it gets a new ending. It's no longer just an alkane, it's an alcohol. And does anyone know what's the ending for alcohols? You don't want to overthink it. Oh well, it's all. All right, so all you have to do, that's why it's really simple. Whoops. You just drop that terminal E and you add an OL. So this becomes cyclopentanol. Now you can give locants if there's more than one, or if it's on a different position than number one. You use di in case there are two. Like we could have it. One example for that would be it'd be called cyclopentane diol because it has two alcohols on it. But we're going to learn more about that later on in the semester. The common name for this would be called, oh yeah.
If it was like diol, would you put the number in before the di? Or would you
So the nice thing about it is in IUPAC, it lets you do it either way.
Okay.
Either, if you put it right before the di, and you keep the E, which is just left over from English, because that way it gives it the long A sound. So they actually put cyclopentane diol a lot of times. But you could put cyclopentane dash like 1,2 diol, or you could put 1,2 cyclopentane diol. But we'll go over those trickier rules whenever you get to alcohols. The common name, by the way, for cyclopentanol is called cyclopentyl alcohol. But once again, once you start adding things onto it, so for example, if we did this, then it would be more cumbersome to start to try to come up with a common name for it. Whereas it's really easy if you learn how to do the locants. If we do the locants on that one, alcohol gets priority, so it's carbon number 1. In fact, it's assumed that if there's only one alcohol on it, it has to be carbon number 1. So therefore, the methyl group would be hanging off of what numbered carbon? 2. So that becomes 2-methyl-cyclopentanol. Now it's perfectly fine, and you can write it out as 2-methyl-1-cyclopentanol. That's fine. Or you can even do what's kind of weird in English. It looks weird at least, but for non-English speaking, like you see this a lot, especially in Europe, is they would sometimes write it out like this. Like I'll just show you. Whoops, it's supposed to be Y. Methyl, cyclo, pentan, 1, all. So, for us, it may be a little weird for us to wrap our mind around, but it literally means that the all functional group is hanging off of carbon number 1. That's part of a cyclopentane. So that's why mathematically, logically, it makes sense. But whenever you're writing it, or if you say it, it sounds really weird to say 2-methyl-cyclopentane 1 all. And so, but that's why you'll see it both ways, okay, especially in international literature. So, actually, I'm just gonna. We already talked all about all of this. So, here. So we're going to start to think about what kind of physical properties alkanes have. We discussed this, I think, a little bit in the very first day, but we didn't go into great detail. All right. So, since it only consists of carbons and hydrogens, it cannot have a dipole. Remember, we talked about the fact that it really doesn't have a dipole, because carbon and hydrogen have about the same electronegativity. Carbon's just a little bit more electronegative, but not enough for it to be a polar molecule. So they are not polar. They are nonpolar. Okay? So because of that, they can't hydrogen bond either. Because it's not like an alcohol or an amine, for those who are starting to learn your functional groups, where you could have an amide or carboxylic acid where you could do hydrogen bonding. Because the carbon is not electronegative enough for it to do a hydrogen bond. However, that being said, I don't actually really like this picture that much. So I'm going to draw my own, don't be jealous of my artistry. But you can imagine, I like to call it the jiggle factor. So we have a molecule here, maybe that's a methane and that's a methane. Its electron density is roughly equally, carbons and hydrogens, and it's roughly spread about equally. However, in reality, the electrons are moving all around. And at a split second in time, maybe it's a femtosecond or whatever, you may have just a little bit more of the electron density on this side than you do on that side. So it's not enough for it to be polar, because it's not really a delta plus. That's why I don't like that one. If you think back to math, maybe you can think of a delta plus, just a really tiny change, but not enough for it to be polar. But because there's just slightly more electron density in that split second, it's going to cause this one, its electron density, to be perturbed as well. In fact, some people call it perturbability. Because what happens is, since there's a lack of electron density there, the methane group next to it could have a little bit more of its electron density. And so that helps hold together. Remember, it's called van der Waals or London dispersion forces. I call it jiggle factor because you can imagine, or at least I was going to say why I like to imagine it, but you can imagine like two pieces of Jell-O. Like if you, at least whenever I went to school back in the 70s and 80s, whenever you were in elementary school and you had like that Jell-O that was really part plastic, you knew it was made of plastic, right? And so there's like the red or the green or whatever, but they were already pre-cut. And so you could have that one Jell-O next to the next Jell-O. Electronically, they're the same, right? But you can have the red piece of Jell-O, if you just touched it and started to cause it to vibrate, it would cause the next one to vibrate as well. And so then the bigger the piece of Jell-O was, the bigger the jiggle factor. And so because of that, it could cause the next one next to it to have an even bigger jiggle factor. Or, when I used to teach, I don't remember if I did in Gen Chem or not, but whenever I taught, sometimes in organic chemistry, I would find that scene of, was it Big Mama's House 2? Whenever he's running on the beach. Yeah, that alone, that'll explain the jiggle factor for you, because it's just wrong. But, so once again, so size matters there. The bigger the molecule, even if it's non-polar, the more it can jiggle. Okay, it has a higher perturbability to it. So it's like that big piece of Jell-O, which would get really wobbly, versus the little tiny one, which doesn't have as much of an effect. Okay, so that's what that picture before was trying to show, I think, and explain. All right. So we have to start to think about, how will this start to affect physical properties? In particular, the one that they talk about the most in organic chemistry is boiling point. Whenever you talk about how stable or unstable something is, they almost always use boiling point, which you've done in lab already. In biochemistry, we don't. Very rarely we talk about boiling point, because under physiological conditions, we're worried about melting point, right? Because for us, if we got hot enough that something was boiling, you'd already be dead. So that's why in biochemistry, we usually discuss things in melting point terms. Organic chemistry, they usually discuss things in boiling point terms, but the trends are identical. It doesn't really matter, because those are colligative properties. So what I like to say is think about spaghetti and spaghetti noodles, because remember, the jiggle factor had to do with the amount of surface area. Because if you had two little pieces of Jell-O, they didn't have much effect with each other because the surface area between them wasn't very big. Whereas if you have a big piece of Jell-O and another big piece of Jell-O, their surface area is much larger, so it can have greater van der Waals forces. So surface area is important. What that means is, if we think about the whole idea of something boiling or melting is where you go from one state of matter to a different state of matter, right? So, for example, at boiling point, we have something that's a liquid, like water, okay, and it starts to boil and it's escaping to the vapor phase. How close together are the molecules in the liquid phase? Are they relatively close compared to the gas phase, or are they... Right, they are. They're much closer together. And so then you can think about when the water has hydrogen bonding and everything else with it. But the two alkanes don't have that ability. The only thing they have is that jiggle factor, the van der Waals forces. So that's why I say think about spaghetti noodles. We could have two spaghetti noodles the same length, the same size. So that way we don't have to worry about size being a factor. If you have one that's long and they're already cooked, okay, one that's long, or you have one that's the same length that you ball it up. So the same number of carbons and hydrogens on each one, and you throw them against the wall, which one's more likely to stick on the wall? The one that's long or the one that's like a ball? The long one, okay. And so that's the same kind of principle here. We can take two identical, I can't erase the spaghetti. We can take two identical I shouldn't say identical, two compounds that have the same formula. For example, pentane in 1, 2, 3, 4, 5, which is 2,2-dimethylpentane, or you could, I'm sorry, dimethylpropane, or you could even say just dimethylpropane because there's no other way to do it. Either one's fine. If we just compare these two, and I would expect you to know how to name these, which one's going to have the higher boiling point? First of all, they have the same number of carbons and hydrogens, right? So now it's which one would have the higher boiling point? The pentane, which is long, or the dimethylpropane, which is like the ball. Which one's going to have the higher boiling point? Remember, the boiling point is just the ability to break the two apart to make them to gas. Pentane. Because you've got, imagine, two long pieces of pentane, you have to add more energy to break them apart. You've got two balls, and it doesn't. They're more likely to bounce off of each other. And so I wouldn't expect you to memorize their actual numbers, but if I give you like a list, what is the possible ones? And I don't know this off the top of my head. You would think, okay, the higher one, since they have the same chemical formula, we don't have to worry there's not an alcohol there. It's not like you're comparing octane and propane, which we'll get to that in a moment. But they're the same. Then it actually has to do with available surface area. That, I wish I would have brought my models out. That one, pentane, has a really long surface area. The propane one, even though it's dimethylpropane, it looks more like a ball. It has a very occluded or very small surface area compared to the pentane. Whoa, that's a highlighter, obviously, not an eraser. And now it won't let me erase. All right, so then let's do a couple. Here, I'll do a different slide altogether. So then we can compare this one and there we go. So the top one, what's its name going to be? Propane. And the bottom one would be called octane. Of the two, which one do you suppose is going to have, this time let's do melting point, the lower melting point? Now you have to think, what does that really mean? What does it mean if it has a lower melting point? Like if I said, I don't know the actual numbers, but if I said one of these was negative 40 degrees Celsius, and one of them would be, 40 degrees Celsius, which one would you suppose is a negative 40? Is it going to be propane, or is it going to be octane? It's propane. And sometimes we get this switched up, but I actually like to deliberately use these two as examples. First of all, you can still think about the jiggle factor, which one's going to be jiggling the most. But think about it at ambient or room temperature, or if you just go outside, is propane normally a gas or is it a liquid? It's a gas, like a propane gas tank. Octane, is it a gas or a liquid? Liquid, it's the octane in your alcohol, not in your alcohol, octane in your gasoline. Okay, so I mean, the higher the octane, because of the fact that it is actually going to be the fact that it's a liquid versus a gas. So that means it has a much higher melting point or higher boiling point too, because they're going to have similar liquid properties there. Okay. All right. I've already answered these. I hit them with boxes. I think drawing it would be better. So if we just think about boiling points for alkanes with respect to molecular weight, this is just a fancy thing of saying propane versus octane. Propane has a higher molecular weight. Octane has a higher molecular weight, so therefore it's going to have a higher boiling point. And the branched ones actually have a lower one than if they were linear. That's the whole idea of the spaghetti noodle, once again. And so all this is showing here is just gives the actual numbers. So, for example, what this is showing is this would be butane. And so methyl butane has a slightly lower boiling point than just regular straight chain butane. And well, the boxes didn't match up on this one anyway. And then the same thing can be said with a similar result with melting points. And so they're showing you the different ones. I wish they would have actually put the degrees on there because I don't know them offhand. But we can imagine that if we looked at the trend, which one of these would have the highest? Is it going to be pentane, 2-methylbutane, or 2,2-dimethylpropane? Right, this would be the highest. This would be the lowest one would be the 2,2-dimethylpropane. So those are the kind of trends to think about. Okay. And the finally, and we already discussed this, is the fact that these are not going to be water soluble. Okay, they aren't. It's like oil and water, because since they are nonpolar and they have the van der Waals forces, they can't hydrogen bond or form any type of polar interactions with water. So they will tend to exclude. They will go ahead and they will exclude water. That's called the hydrophobic effect. Okay. So what happens is anything that's hydrophobic, like that's nonpolar, will come together. It excludes water, and the water will be on the outside. Of course, our body utilizes this to its advantage. Think about what part of our body deliberately uses the hydrophobic effect. Well, there are multiple parts, but what's one part? Pardon?
Skin.
Yes, your skin, right? Because otherwise, every time it would rain or whatever, we'd melt or it'd just go right on through. Right? So it excludes water. You can think about just even on a simple level, the cell membrane actually has an interior has a hydrophobic interior. And so that's why it can keep liquid on the inside of the cell and liquid on the outside of the cell, but in the membrane, it doesn't have liquid. Or you can think of proteins, and there are lots of different possibilities here for to talk about hydrophobicity. That's that ability. It's called hydrophobicity. Just like hydrophilicity is the opposite. All right, so now those were all like physical properties. Now we're going to be talking about the chemical properties. And alkanes in and of themselves many times are relatively inert, with one exception is they can combust. That's the reason why you can use propane gas for energy. Okay? You can use octane for gas. So what happens is your alkane mixes with atmospheric oxygen, it gives off carbon dioxide and water. You've learned this probably all the way back even in biology with the whole idea of respiration and burning and all that kind of stuff. But it also explains the reason why you typically don't use like propane, to drive your car. You get more energy out of octane because there are more carbons that can be oxidized. All right. So this just shows an example here. This is enthalpy. I'm not going to go into a lot of details with it. Remember, it's negatively charged, not charged, I'm sorry. I was going to use the wrong term. It has a negative sign. Do you remember why does it have a negative sign? It's giving it off. Remember, it's with respect to the system. So since it's giving it off, it's negative with respect to the methane or the propane or pentane or octane. So that's why this is where it kind of confuses some people. The more negative it is, the more energy is given off. So therefore, the more energy you could get from it. So that's why octane would have a much higher, the absolute value would be much higher for octane than it would be for propane. They would both be negative, but it'd be even more negative. And so the way that the way that we monitor this is we use oxidation. So that's heated combustion. Those are just numbers for it. Okay. But they use something called oxidation numbers in order to see if something's being oxidized or reduced. So let me go through here and just give an example. This is the idea you probably remember. Like Leo the lion goes grr, or oil rig, or something like that. Because losing electrons is oxidation, gaining electrons is reduction. Or if you think of oil rig, oxidation is losing, reduction is gaining. But we have to be careful here because many times the actual it's not changing its formal charge. And so people, I've seen this time and time again, people confuse formal charge, which is something you have to do for every single time that you draw a Lewis structure, versus an oxidation number. All oxidation number is electronic bookkeeping. It's trying to figure out where more of the electron density went. It's not an actual charge. Okay, sometimes they coincide, but many times they don't. Okay, so that's why carbon, for example, can go all the way from a -4 oxidation number to a +4 oxidation number, but it's never charged. So that's why, and the book gives off like a shortened version of the rules, but I'm afraid that it would be kind of, it's not always useful. So this is the way that you can figure out the oxidation numbers for something. So what I'm going to do is, this is one of the few times I'm going to draw everything out. So for example, I'm going to draw out just ethane. Okay, that's just ethane. We're going to figure out the oxidation number for this. Now, the first step, like, until you can learn to do this in your head, the first thing that you're going to do is you're going to draw all of the electrons, like the individual electrons. Of course, hydrogen doesn't have any lone pair electrons around it, so you don't have to worry about that. But when we redraw this, so I'm going to draw the 2 carbons, and I'll even change the colors, that way we can tell the difference between the carbons. And we have the hydrogens around them. Okay. Now what we're going to do is, for this bond, for example, the bond that would be here, those 2 electrons, we give both of them. This is only for bookkeeping. This doesn't really exist. We give both of them to the one that's more electronegative, even if it's slightly more electronegative. So, which is slightly more electronegative, a carbon or a hydrogen? Carbon, just a little bit more. And so we would say, oh, both of those electrons go to that carbon. Same thing with the hydrogen that's on the left and the hydrogen on the bottom. And the same thing will be true for this carbon. So which should make sense. These carbons are identical. However, now we have to think about, what about the electrons that's between these 2 carbons? Is there a difference in electronegativity? No. So that means they each get one of the 2. So 1 electron goes here, 1 electron goes there. Now to figure out the oxidation state, this is not a formal charge, this is the oxidation state. Now the math is pretty much the same. So if all the hydrogens are identical, so I'm just going to do 1 for hydrogen. What you do is you take its valence number, like this valence number of electrons, which is 1, minus the number of electrons that we have drawn around it. And so if you notice these, it's more obvious, I think, on the one on the left-hand side. There are no electrons around that. So it's 1 minus 0. So that means it's got a +1 oxidation number. It's not charged. It's neutral. Ethane is completely neutral. Now when we do the carbon, and it doesn't matter which carbon we do because it's the same, what's the valence number of electrons for carbon? The valence electron. It's just 4. That's on the outside. But now if we count here, each one of these carbons has 1, 2, 3, 4, 5, 6, 7. So 4 minus 7 is -3. So the oxidation state for that carbon is -3. It's not negatively charged at all, but that's its oxidation state. Well, now what happens is, if we wanted to burn here, now we're going to burn, let's say we burn ethane for energy, so it's given off in carbon dioxide. Okay? So you draw a carbon dioxide out, it's going to look like this. Once again, I'm not going to skip any steps. Now I'm going to do split up the electrons. We have a carbon. We've got 2 oxygens. Both of the oxygens already had lone pair electrons around them, so they own both of those regardless. But now if we look here at the carbon, Which is more electronegative, the oxygen or the carbon? The oxygen. So that means this oxygen right here gets all 4 of these electrons. And same thing on this other side. So whenever we do the oxidation number to figure out the oxidation state for the oxygens, so this is oxygen, not the number 0, because otherwise this math is going to look really weird. What's the valence number of electrons for oxygen? 6. And the way that we've drawn the oxidation drawing here, how many electrons are around it? 8. So 6 minus 8 is -2. And likewise, we can do the same thing for carbon, which we already said that carbon, that's why I said that that's not a 0. Because if you go back later on in your notes, it's like, why 0 is not equal to -2? You know the mathematicians would just be cringing. All right, but no, carbon here, we already said that's 4, but how many electrons are around it when we redrew it for the oxidation number? It's 0. And so 4 minus 0 is 4. So that's, I just wanted to point this out because I specifically picked ethane, and when you burn it to form carbon dioxide, the carbon's oxidation state goes from a -3 to a +4. So the net difference is 7 electrons. Now, that's with respect to the oxidation state. It's not charging, it's neutral in both. So is that carbon being oxidized or is that carbon being reduced? Did it lose electrons or did it gain electrons in the process? It lost. So it's oxidized. It's pretty easy when we're doing it here because so the little cheating method to tell if something's being oxidized or reduced for carbon is if it increases in the number of carbon to oxygen bonds, it's being oxidized. If it's increasing in the number of carbon to hydrogen bonds, it's being reduced. Likewise, there's some other shortcut. I hate saying cheating because it's just a shortcut way of doing this. Hydrogen, unless it's bound to a metal like sodium or boron or something like that, hydrogen is always a +1 because it's always less electronegative than anything else. So it's always a +1. Oxygen, unless it's bound to another oxygen, it's always a -2. So that's why you can figure it out because oxygen is so electronegative. The halogens, unless they're bound to oxygen, the halogens are always going to be -1. And so that's why you can get to where you can figure out much more quickly. Because you can just look at it and say, okay, that hydrogen has to be +1. Carbon is really the one that changes so much, but you can always figure out the actual oxidation number, but just count the number of carbon to oxygen bonds or carbon to hydrogen bonds. I say that because, let me see. I just wanted to point this out, and this is what I'm going to end with today, is if you look, this is methane, which has a -4. This is carbonic acid, which is as oxidized as it can get, and it gets all the way up to a +4. So that's why this is being oxidized, going this direction. Going that direction is being reduced. Okay? And your body does this in vivo all the time. It's just that we can't set ourselves on fire. Please do not set yourselves on fire. Okay. So, but our body has enzymes and other ways of doing that. Because every time you exhale, like right now, I'm exhaling carbon dioxide, it had to come from somewhere. All right, so I'm going to go.